YouTube. There we go. So I'm starting the stream right now, and also, my own webcam is blocking the view. So now I'm just moving it so that it's not being blocked. Okay. As you might remember, this is the graph that we talked about last time. So it's basically exactly the same graph, except this time we also have heuristics, the heuristics to deal with. So I'm just going to write right below the graph, what the heuristic functions or the heuristic values are. So we have HAD being 4, we have HBD being 0. Oh, right. Okay, so let me do that too. Give me a second here. There we go. All right, now it should be shared. Thank you. Thanks for letting me know. Oh, but somehow the viewer is not being updated, so I have to restart that one twice too. So as I was trying to explain to someone, I was at the I was at the cascading end of a series of unfortunate events. The silver lining to all of this is proof that being able to work on mainframe computers, either as an administrator or even as a developer, is actually highly desirable for the state and many other large organizations, such as American Express, Walmart, or locally the supermarket chain, Raley's. I believe they also use IBM mainframe computers in the back end. Wells Fargo too. So all of those will be interesting. YouTube is down too. Let me see. Alright, so let me go take a look at the live stream. Nope, YouTube seems to be up. I am streaming right now, so I think it should be working. Alright, so getting back to here, I'm going to copy h of CD is 1, and then h of DD is 0. Okay, there we go. Alright, so now we can start to work on the algorithm. And I'm going to do it about the same way as last time. Basically I want you guys to open up your own page for the algorithm, and so this way I can use the screen share area only for the spreadsheet, and you can refer to the algorithm on the side. Alright, so we'll go back to the algorithm first. Alright, it's under graphs, and I'll post the link too so that you guys can just click on the link and be able to get there. Alright, so the link is being posted on the text channel in Discord. So if you just click on that one, it will get you to the A-star algorithm directly, which is what you're seeing here. And we are going back to the assignment because I want to use the same Google Sheet that you're supposed to start with. So we'll get to the assignment and click on the Google Sheet. And as you can see, this Google Sheet is a little bit different. It has function G, function F, and prev, as opposed to the Dijkstra one, which does not have these specific functions or columns. So the first thing, I'm going to work on this using a local spreadsheet. So I'm going to download the file first and then open it in LibreOffice. The trace that you're going to do is actually fairly short, so it's not going to be nearly, not even as long as the one that you see over here. Alright, so here's my spreadsheet, and I have to make this always on top again. There we go. Alright, so now we got everything that we need to start to trace the algorithm. And I'm going to zoom out just a little bit so everything fits on the screen. We don't have vertex D. Excuse me, we don't have vertex E. Vertex D is our destination, which is also the last one. So let me see if I can just remove a column, even though it is already merged with one of the cells. So we'll go delete columns. Yep, okay, that works. So I'm going to remove this one too, and also this one over here. There we go. And now we can kind of go back and redo the initialization. So we're going to remove the content of all of the cells, and we're going to start from scratch. Alright, so assuming that you have the algorithm on the side, which I'm opening up myself here, we'll look through the initialization first. So for the initialization, yeah, I'm just repositioning my screen so I can still see the Discord text messages when I read the algorithm. There we go. Okay, now I can see everything. Alright, so in the A star algorithm, the initialization is starting on the for each line, which is like the 1, 2, 3, 4, 5, 6, the 6 bullet points from the top. So we basically just want to initialize the P, the G, the V, and also the prev of each vertex. The G is basically telling us what is the length of the shortest path from the source, the origin, to this particular vertex. Now A is our starting point, and it is in so that's why the G value of A is 0, and then the F value is the estimated length of the shortest path from the start vertex through a particular vertex to the destination. So in this case, we would have to rely on H of AD to add to the G value to give us an estimate of the shortest path, the length of the shortest path from vertex A to vertex D. So it would be 0 plus 4, which is just 4 itself. And for all of the other vertices, they all have infinity as the G value because we have not explored anything within the graph. So we don't even know whether vertex B is reachable from vertex A, and the same applies to vertex C and also D. And as a result, because the F value is the G value plus the heuristic value from a vertex to the destination vertex, and that's why they're also just infinity. The prev in this case, they are all undefined or unknown. Okay, so we can either use UNK for unknown or undefined, which is UND. Both are okay, because we just have to indicate that we don't know. We simply do not know, in the shortest path, who is going to be right before which other one. All right, so that takes care of the initialization, which is the for each loop in the algorithm. And now we initialize the set of O to start with the start vertex. In our example, the start vertex is vertex A, so we just initialize O with A as the only element in it. So now we can finally get started with the algorithm, starting with the while statement. So as I explained in the previous class, the while statement is not checking whether the set is empty or not. Okay, it is checking to see if there are anything, see if there's any vertex in the set O in this case that has the F value being less than the G value of the destination. So that translates, okay, I hope you guys also spend some time to think about what does that mean. What that means is we potentially still has a shorter path compared to the one that is already discovered, if there's one, to go from the source to the destination. So we look at vertex A, we look at the f value of vertex A, and that is 4. This basically means, optimistically speaking, okay? Optimistically speaking, we think that there might be a path that has a length as short as 4 from vertex A through vertex A to the destination vertex. Okay, that technically that's what the f value is telling us. And then we look at the g value of d, which is the length of the currently known shortest path from the start vertex to the destination vertex. And right now it's infinity, which is basically telling us that we have not found any path from the start vertex to the destination vertex. But the value of quote unquote the value of infinity kind of serves the purpose, right? Because it basically says, it's really a big gigantic value, okay? Because we haven't really found anything. So we say, yeah, sure, f of a is 4, and that is less than g of d, which is infinity. So we get into the loop. Once we get into the loop, we have to find one of the vertices in O that has the least f value of all of the vertices in O. In this case, it's easy, right? Because O only has one single vertex, which is A. So that has got to be the one that we're going to choose as variable C, as the value of variable C. And then the next thing we do is we just remove that particular vertex from the set O. And then we get to the for each statement. Unlike Dijkstra's algorithm, which look into the incoming edges into the vertex that we have picked out, this one explores all the outgoing edges from the vertex that we have picked out. So we are evaluating the two edges. One is from A to B, and then the other one is from A to D. The order is not important, so I'm going to intentionally mess up the order, the quote-unquote natural order. So I'm going to pick out D first. So I'm looking into the edge AD. And then inside the for each loop, the first thing we do is to compute the value of T. So the value of T is G of C, and since C is A, so we're looking at G of A, which is 0. And then we add to it the distance of the edge AD in this case. So the edge AD has a distance of 11. So we have 0 plus 11 as our local variable T. And now we evaluate the conditional statement. The conditional statement says if T is less than G of N, then we do blah, blah, blah. Okay, so let's check out G of N. N is D right now, so G of D is infinity. So we are really asking whether 11 is less than infinity or not, and the answer is yes. Okay, 11 is less than infinity. Then we proceed to the then branch of the conditional statement. So that's what the algorithm says. But what does it mean? Why are we comparing these two particular values? What T is representing at this point is the length of a path from the start vertex to vertex D in this case. Now, I specifically use the term a path, not the shortest path, because all it says is, oh, we found this way of going to vertex D from vertex A, okay, and the length of that path is 11, okay, for sure. So now we look up G of D, okay, and because G of D is representing the length of the currently known shortest path. So we want to see if we have discovered a shorter path than the one that we have found. And the result in this case is yes, okay, because 11 is less than infinity. So we found quote unquote a shorter path because this is really the first path, but we can call that a shorter path. So now we get into the then branch, which has several things to do. We're going to have to add this element D to our set O. Okay, so the first thing we do is to update O here. so that it now has element or vertex D as its element. The next item is to update the prev, the previous. So the previous of D, in order to represent this path, the preceding vertex to get to vertex D is going to be vertex A, so we put A over here. And then we update G of n to be just T, because remember T is representing the length of this new path. Since this new path is the shorter path, we update the G value to the value of T. And then last thing we do is to update the estimated length of the shortest path from the start vertex through vertex D to the destination, which is also vertex D. So we have to add to G of D the value of H of DD, which is 0. And that makes sense, right? Because the heuristic value cannot exceed the length of the shortest path between those two vertices. Now, because D is D, so there's no path to talk about, or the path has a length of 0. And as a result, the heuristic value cannot be anything other than 0, because you cannot have a negative value as a heuristic value. That just doesn't make sense. Alright, so that completes one iteration of the for each loop. Now we go for the next iteration of the for each loop, because there are two outgoing edges from vertex A. So now we go for the second edge, which is from A to B. So now we have to compute T again. So once again, we look at G of A, and then we add to it the distance from A to B. So we have 0 plus 1, which is 1. So T is now having a value of 1. And now we have to ask a similar question that we asked earlier already, is are we discovering a shorter path from A to B in this case? Well, we can do the comparison. Tell me what is the length of the shortest path right now from vertex A to vertex B. Well, that length turns out to be infinity. And the length of the current path, the alternative path, has a length of 1. Is 1 shorter than infinity? The answer is yes. So now we have to go to the then branch again. First thing we do is we add B to the set of O. So now O has B, D as the two elements in it. Next, we update the prev, which is the previous. So in order to get to vertex B, we come from vertex A. And then we update G. G of B is going to be the same as T, which is 1. And then the F value, this time it is more meaningful, because the F value of B is asking, what is the optimistic estimate of the length of the shortest path from vertex A through vertex B to vertex D? So that's based on the heuristic function here. So the heuristic function, or the heuristic value of BD, turns out to be 0. So F of B is also updated to 1 at this point. Do we have any questions? Okay, no questions. All right. So that completes. Oh, I just used the wrong row for all the updates. Let me just move all of those to the next row. Okay, so we'll just copy and paste all of this stuff here. Cut and paste, actually. Cut and paste, because they should be on the same row as the update of the set. So that concludes the for each loop. After the for each loop, there's nothing else to do in the while loop, so we go all the way back to the beginning of the while loop. So once again, we have to evaluate the while loop carefully, because it is asking, do we have any vertex in the set O where the F value of that vertex is less than the G value of D? Now the G value of D is no longer infinity, it is 11 at this point. So now we are asking, basically, does any one of the vertices in O have a F value that is less than 11? The answer is, yeah, we got one. It's vertex B, because vertex B has an F value of 1 at this point, which is less than the G value of D. So we still have hope that we might be able to find a path that is shorter than 11, because that's basically what the f value is doing, is it is giving us a optimistic estimate of the length of a path. And something does look optimistic, being this 1 over here. So now we get into the while loop. The first thing we do in the while loop is to find the vertex within O that has the least f value. So of the two, one is B and one is D. So B has an f value of 1, and then D has an f value of 11. So we're going to pick B. And now we look at all the outgoing edges of B. There's only one. Oh, there are two. So there are two outgoing edges from B. One is to vertex C, and the other one is to vertex D. We'll deal with C first this time. Okay. So now we have to look at the sum of g of B and the distance of BC as an edge. BC as an edge has a distance of 2, and then the g value of B is 1. 1 plus 2 is 3. So t is 3 in this case. And then we have to compare 3 with the g value of C right now, which is infinity. It is less than, so we have to go into the then portion. The then portion is going to add vertex C into the set O. So now, oh, I forgot one thing here. I forgot to remove B from the set first. There we go. And now we have to add vertex C into the set. So the set now has vertex C and vertex D. And then we have to update the previous so that we can remember to get to vertex C, we come from vertex B. So that would be here. And then we have to update G. G is easy to update because we just copy and paste the value of T, which is 3 in this case. And then the F value is the G value of C plus the heuristic from C to D. The heuristic from C to D is 1, so we have 3 plus 1, which is 4 over here. Do we have any questions at this point? No questions? All right. Then we go for the next iteration of the for each loop. Oh, wait, there's a question coming. I'm gonna wait for the question before I continue the trace. All right, so the question is, not really quite sure what that statement is saying. Okay, I'm guessing it is referring to row 6, and the f value is g of. Okay, so there's no such thing as h of 4. The heuristic is always between two vertices, and 4 is not a vertex. We have vertex D, so I'm not really quite sure what that part is asking. There's no g of 4 either, because there's only g of A, B, C, D. Not really quite sure what that question is asking. I'm gonna guess f of D is 11, and then the heuristic value of D to D is 0. It is not 4. Yes, okay, I see that. I see column L is 11. Why would it not be 11? Because according to the algorithm, the way we update the f value is g of n plus the heuristic of n to the destination vertex. But why are we concerned about h of a, d in this case? Where are we getting the vertex a? the heuristic is between n and x. N is vertex D, x is the destination vertex. So the h of d to d is 0. So a has no part in this particular calculation. So that's okay. So what that is telling me is it is important to read the algorithm carefully, because what the variables are referring to are very important. Yeah. Okay. All right. Okay. So let's move on. All right, so we have just explored the outgoing edge from B to C. Now we're going to explore the other one, which is from B to D. So now we say, okay, we are going to evaluate B to D. So that makes the value of n, vertex D. And now we have to compute the value of t, which is g of b plus the distance from B to D. G of b has not changed since we updated it earlier, so it's still 1. And then the distance of the edge BD is 3. So we got 1 plus 3, which is 4. So we got a 4 here. And now we have to ask, what about did we find a shorter path? Okay, that's basically what we're trying to ask. Okay, did we find a shorter path from the start vertex, which is vertex A in this particular example, to vertex D? So we have to compare t with g of d, which has a value of 11. 4 is indeed less than 11, so that means we have to go into the then portion of the conditional statement. So the then portion of the conditional statement is first going to add vertex d into the set of O. Okay, so it basically does not change because you cannot have duplicate elements in a set. But I'm going to write it here as well, might as well. Next thing we do is to update the previous. So the previous of D was A, because that was the first path that we found to vertex D. But now that we have found a shorter path, we're going to have to update the pref of D so that it is now updated to B. There we go. And then we update the G value is copied from the T, the local variable T, which is 4. And then we also have to update the f value of the same vertex, which is the g value of that vertex plus the heuristic of that vertex to the destination. Well, guess what? We are looking at vertex D, and it is also the destination. So the heuristic function is guaranteed to be 0. So 4 plus 0 is also just 4 right there. And we are now done with the last iteration of the for each loop. We go back to the beginning of the while loop. So now we are now staring at these two vertices, and then we ask, does any one of these have a does any one of these have a f value that is smaller than the g value of d? So we look at f of c. F of c is 4. And then we ask, is 4 less than g of d, which is also 4? The answer is no. Then we look at d. We look up the g value of d, which is, we look up the f value of d, which is 4. And then we ask whether that is less than the g value of 4, which is also 4. 4 is also not less than 4. So now, none of these two vertices has an f value that is less than the g value of d. And we're done with the loop. This is the end of the trace. Okay, we got some questions coming. Exactly. So what Angel said is correct in the text channel, because they are the same. They being the f values of C and the f value of D, they're both 4, and therefore they are exactly the same as the G value of D, which is also 4. And as a result, there's nothing promising anymore, okay? And as a result, we're just going to exit the loop, because the f value of all the vertices in O are saying that well, you can try, okay? You can try to explore additional paths, from the start vertex through one of the vertices in O to the destination vertex, but none of those is going to have a shorter length anymore. That's basically what this condition is saying. And as a result, the algorithm ends right now. Okay, so you look at this and go like, okay, but how do we reconstruct the shortest path? Well, it's by backtracing the pref. You start with the destination vertex, which is D, and then you look at that and go like, okay, who should I go back to from D? It is B. So you look up B at this point, and then B says, okay, to get to B, you should start with A, and then you look up A. A is the start vertex, so it doesn't have a previous vertex. So we know the shortest path is from A to B and then to D. So if you look at the actual graph, from A to B to D is indeed a shortest path. Now note what I said. I said a shortest path, not the shortest path, because you can also go from A, B, and then C, D. That would give you the same length, but we are not using that path because the algorithm has already found the shortest path, the length of it already has found one shortest path. So even though there's an alternative shortest path, that one would not be explored because it has one more hop in this case. All right, so we got some questions in the text channel. Okay, that's good. A star finds the shortest path, but there are alternate paths of the same distance, of the same length. Would there be a use case scenario where the order or instance of the first discovered shortest path matters? The answer is it depends. If your only objective is to find the shortest path, then you don't need to find the alternative, right? Because the one of the shortest paths is still a shortest path, and it makes no difference whether you go for one or the other ones, right? So from that perspective, it doesn't really matter that you have other paths of the same length. They're all quote-unquote shortest. Just locating one of the shortest path is sufficient already. Now, that being said, there are other types of analysis of a graph where we want it to be robust. Okay, we want to remove bottlenecks, or how do we call those things? Critical paths. Okay, we want to remove critical paths. Basically we want to have multiple ways to get to from the source to the destination, just in case something happens, right? So in those cases, okay, it might be helpful to identify, what if this path does not work? Okay, what if there's an accident and this street is blocked? What is the next shortest path? But that typically is not an issue because by the time we discover the accident, we would also change this 3 to infinity if it is completely blocked, or if it is just heavily congested, this number would bump up to like 30, 40, 50, or so on. And then we just rerun the A star algorithm, and then we'll find the other path, which is A, B, C, D. Now, what if CD is also blocked, right? What if there's also a traffic accident between C and D, and that bumped up the distance from C to D to 100, okay? Then we would rerun the algorithm, and in that case we're going to find A to D being the shortest path. Even though initially it was the longest of the 3 paths, now it becomes the shortest. But the whole point is, as we discover those blockages, the car accidents and whatnot, we would be updating the distance functions, and as a result, by rerunning the A star algorithm, we would then find the alternative, shortest path, because the original shortest path is no longer valid because we updated the distance between the edges. We updated the distance of the edges as we discover car accidents and whatnot. All right, next question. Maybe just programming routes to prioritize staying on the same road before making a turn. Okay, so in that case, you have to encode turns into edges. In other words, if making a right turn takes average, let's say 1/3 of the time of making a left turn, then making turns, the turns will become edges as well, because you have to take the turns into consideration when you are looking at the actual time of going from point A to point D in this case. So it becomes an encoding issue, but the algorithm still runs exactly the same. So in addition of coding, like going down a street from one intersection to another intersection, instead of just having those represented as edges, now you also have to encode making turns into edges too, so that you can take that into consideration. Does that answer the question, Angel? Those are very good questions, because it's a matter of how do we encode information into the representation of a graph. Alrighty, excellent. So do we have any additional questions about the A star algorithm? I mean, this is the whole trace. This is actually, it's actually shorter compared to Dijkstra's algorithm because we are finding only the shortest path between vertex A and vertex D, whereas the other one is finding a shortest path from every vertex to a destination vertex. So the nature of the question is a little bit different between the two algorithms. Alrighty, no questions. Alright, so if there are no questions, then we're going to go back to the question that we had on Monday. Okay, so first thing, I have to go find it first. Let me go to the other text channel, the text channel for the other day, because I think I posted a link in that particular class. And that would be the 10th of May. Oh, it's right above. I scrolled, I went to the archive days, but it wasn't in the archive days. Alright, so let me look up the pinned messages. So that would be question number. Oh, I did not pin it. Alright, so where did I put it? Oh wait, I take it back. All right. I forgot that I concatenated all the questions already, so I thought the file only had one single question, but it actually has all three questions in it. So give me a second to open that up. And this was fx-00 1.txt. There we go. All right, so I'm going to put the exam question up here. I know it's too small. I'm going to bump up the font size. All right, so we got the first question done already. And these are still the first question. And then we got the last question done. This is the question in the middle. Okay, so what I'm going to do is to make use of the tablet. All right. So let me move the tablet into here as much as I can. And then we're going to try to fit the entire screen in because I think this time we might need a little more space. There we go. And I have to make sure that I am not blocking any part of the graph. So I'm going to move this down a little bit, like so. There we go. All right. And I'm going to start with a new page, and and also use a thicker pen because I think this pen is way too thin. It becomes difficult for us to see the actual um, diagram. All right. So remember, this is a trace of Dijkstra's algorithm. We just went through A star, so I can understand how it can be a little bit confusing. So we are now going through Dijkstra's algorithm, and it would be helpful if you have the Dijkstra's algorithm open on the side, so you can refer to the algorithm. What it's telling us in the initial condition is because Q has an initial value of n8 and n1 in the set, so that means we have two destination vertices. One is n1 and the other one is n8. So as a result, we'll go ahead and specify n1 and an n8 as our destination vertices. And then we pick n1 first. I take it back, sorry. We picked N8 first. Now N8 and N1, because they're both destinations, they're going to have the same L value. So we know, it doesn't really matter. There's no ordering of L values between N1 and N8 because they're both destinations. So right now we don't have any ordering information. And then we look at all the incoming edges to N8. N8 has one incoming edge coming from N3. So at least we know that N3 has an edge going to N8. Now we don't know what value, what distance we should assign it to, but we know there's an edge. And we can start to use variables, to label the distances. So I'm just going to call this A, okay? As a value of that particular the distance of the edge. The next edge is N7, N8. Okay, so N7 also has an edge leading to N8, and we'll call the distance of the edge B. Let me go back to today's text channel. I don't think anyone has typed anything yet, but just want to be sure that I'm going to catch all the text messages over there. Okay. Let's see. I can actually make this a little bit longer. I wasn't making use of the entire as much area as I can. Okay, this is good. So now we can use more areas. More area, not countable. And we also have N6 going to N8. Okay, so we have N8 going to, oh wait, N7, sorry. Erase. So we have N7 also having an edge to N8. We'll call the distance of this being C. And as a result of having those incoming edges, Q is going to have all of those edges added to it. So we can see how, after we discover the edge N3 and N8, N3 is now in the set of Q, and then N7 is added, and then N6 is also is also added. Oh, okay, sorry. I messed it up. Sorry. There we go. We have N6 here. Thank you. All right. So that concludes all the incoming edges to N8, and we know N1 is also a destination vertex. So right now we also do not have any. Well, we may not have any ordering information. So we take a look at all the incoming edges to N1. So we have N5 going to N1, we have N0 going to N1. So right now we do not have any overlaps, right? So we have N, what is it again? N5 going to N1, okay, right there. And then we also have N0 going to N1. So we have N0 going to N1. And then we also give these a letter for the distance of the edge. This is going to look confusing. I'm going to use the letter D, not to denote the function D, but just as a value of that particular, of the distance of the edge. And then we're going to use E over here. So right now we don't have any ordering information whatsoever. Okay. But as we proceed, let me go back to the line here. So as we proceed where my text cursor is located, out of these five, none of these is a destination vertex anymore. So so these have non-zero. Well, I shouldn't say always, but potentially they're all non-zero L values, and we chose the one of n3. So that sort of let us know that n3 may not be less than all of the other ones, but it's certainly less than or equal to all of the other ones. Okay, so now we kind of look on the side here, and then we basically say n3 is less than, oh, I shouldn't say n3 here because we are referring to the distance. So n3 has a distance of a, so we say a is less than or equal to a whole bunch of other values. So it's going to be less than or equal to b, c, d, and e. Okay, let me just pause here and see if that makes sense to you guys. So right now, because we chose n3 to become the variable v, and because of the algorithm always choosing the vertex in Q that has the least L value, I can now claim that A as a distance of that edge from n3 to n8 is going to be less than or equal to all of the other unknown values that I have put up in the graph, namely B, C, D, and E. I just want to make sure that this makes sense at this point, because if this does not make sense, then the rest of this reasoning is not going to be helpful in any way. So are we doing okay so far? Okay. Not seeing any questions. All right. So some people may be tempted to start to assign a number to A, like, we can just make it 1 so that, we can now see, because it's easier to look at a concrete value and say B is at least 1, C is at least 1, D is at least 1, and then E is at least 1. But I'm not going to defer that until I know more. And if you're thinking that I have the solution sitting somewhere else on the screen and I'm just copying from the solution, that is not the case. Okay, I'm really working on this problem as if it is a new problem to me. All right, the next one we choose is n0. So if you look at the graph, n0 to n1 has a distance of e. So we kind of can tell that e is less than or equal to the other three unknown variables. But before we go there, there's one more thing that we need to know. Because we are now looking at the edge of n7 to n3. So we know there's an edge from n7 to n3. n7 to n3, there's an edge here. Okay, so that is important because we are using every single thing we can get out of the trace of the algorithm to basically reconstruct the graph. And we're going to assign another letter to represent the edge or the distance of that edge from n7 to n3. So we're down to f at this point. There we go. All right, so now so this part is important. So now we have to look at the choice of n0 here. Okay, and then we ask, okay, what information is this telling us? So what it is telling us is L of n0, which really is just the edge from the distance of the edge from n0 to n1, which is basically e, is less than or equal to the L value of the other three. So the L value of n7, the value of n7 is updated here. So this is also significant. Because the L value of n7 is updated, which also tells us that the L value of n3, at this point is, so it might be helpful to keep track of the L values too. Okay, so the L value of n3 is just A. So that's telling us that A plus f, okay, so it's telling us that a plus f is less than, hold on a second here, right, okay, so it is less than b, basically. There we go. All right, so let's find out whether this makes sense or not. Okay, so I'm looking at this inequality here. At this point, where the cursor is, the L value of n3 is really just the just a itself, and then the distance from n7 and to n3, n7 to n3 is f. So we are looking at a plus f in this case. And that turns out to be less than the L value of n7. And at this point, L7, L of n7 is just b, because that was the first L value of n7 is just b. And that's why, if we get into the then portion of the algorithm, it's telling us that a plus f is less than b. Are we doing okay? Because this is really important. I want to kind of pause here and make sure that everybody understands this part. All right, so I'm not seeing any questions. Okay, so at this point, I'm going to have to start to keep track of the L values too. So we're going to have to say L of n7 is a plus f. Okay, and that has to do with we update L of n7 right here, which is right after we perform the comparison, and the comparison is confirming that the greater than relation is true. Okay, so that this part is important. And then we have another choice of n0. So we are choosing L of n0 being less than the L value of all of the other ones. So at this point, n0, L of n0 is still just e. So now we are confirming. Okay, let me erase this one here. So we are now confirming that e is less than or equal to a whole bunch of stuff. Okay, 3 of them in fact. It's less than or equal to the L value of n7, and we know that n7 from here is a plus f. It is less than the L value of n6. The L value of n6 is just c at this point. We also know it is less than or equal to the L value of n5, and n5 is just d at this point. So now we're just adding more to the graph of relationships. Are we still doing okay at this point? Because I want to make sure that I'm not losing anyone at this point. But basically, we are just adding more and more to the relation between the expressions. We start off with very simple ones like single variables, and now we're starting to have summations. And at the same time, we have to keep track of what is the actual expression of each L value. So now we evaluate, because n2 is an incoming, n2, n0 is an incoming edge to n0, and n2 has not appeared yet. So we have a new vertex here. This is n2 to n0. And as a result of that, the initial L value of n2 is infinity. So that's why we found a quote-unquote new value, L value of n2. And it is useful to denote this as g. And now we say L of n2 is g plus e. Okay, so it's important to keep track of all of that stuff. I just want to see if, okay, there are no questions. I think I'll stop asking, are there any questions? If you guys have questions, just go ahead and type your question in the text area. Because, there are people who ask, I hope this is not a stupid question, but I think I feel stupider by keep asking questions. Do you guys have any questions? So if you have questions, just go ahead and type it. All right, so now we are down to N7, N6, N5, and N2, and this time we're choosing N6. Okay, so we have to look up the L value of N6. Now N6, has only one single edge, going to N8 at this point. So the L value of N6 is still really just C itself. So now we know that C is less than three things, less than or equal to three things. Is less than or equal to the L value of N7. And L of N7 is still just A plus F. Okay, so we just type A plus F over here. It is also less than or equal to the L value of N5. N5 is right here. So the L value of N5 is really just D. And it is also less than or equal to the L value of N2. N2 is the one that we just discovered, and the L value of N2 is G plus E. There we go. Right. Okay, so now we are looking into, we picked N6, right? N6, I'm just double checking. Yeah, so okay, so I didn't make a mistake. So now we're discovering there is an edge from N2 to N6. So N2 is here, N6 is over here. We'll call this H, which is not in any way related to the heuristic function. I'm just picking a letter to represent the distance of an edge. Okay, in this case, it is H. So we are looking at H, which is D of N2, N6, and we add it to L of N6. L of N6 is only C, so we are looking at C plus H as a sum. That sum turns out to be smaller than the L value of N2 at this point. The L value of N2 at this point is G plus E. So now we know that G plus E is, okay, so I'm going to write it down here. G plus E is greater than the new one that we found, which is H plus C. There we go. All right. So now we're basically confirming all of these inequalities, as we kind of process the trace. All right. So this one is processed, and as a result, N2 is, quote unquote added to the set Q, but since it's already in the set Q, it doesn't seem to be added into it because it's already there. All right. So now we are down to N7, N5, and N2, and we choose N5. So now we look up the L value of N5. Oh, I forgot to add to that one, which is L of N2 is no longer G plus E, instead it is H plus C. So it's important to keep these things up to date, like that. All right. So now we choose N5. So we now know that N5, L of N5 is D. So we know that D is less than or equal to two things. Okay. So the two things it is less than would be the L value of N7 at this point. So we know it is, the L value of N5 is less than the L value of N7. And N7 is A plus F at this point. So we know that D is less than A plus F, which is the L of N7, and it is also less than or equal to the L value of N2, and the L value of N2 is H plus C at this point. H plus C, okay? Because that is how we chose N5 in this particular while loop iteration. And we discover a new edge from N3 to N5. So now we draw an edge from N3 to N5. Here's N3, and there's N5 right there. GH, this is I, okay? So we are not updating, okay? So we are not updating the L value of N3, which tells us, the result of a comparison, right? Because, it's telling us that we did not discover a shorter path. And as a result, we can now claim that L of N3 at this point is just A, okay, is less than or equal to, so we say that A is less than or equal to I plus D. Okay, so this part is a little bit tricky. I'm gonna give you guys a few seconds to think about what I just said and see if that makes sense to you. Okay, I'm not seeing any questions. Alright, then I'll proceed and move on. Okay, now between N7 and N2, we chose N2. So we have to look at the L value of N2, which is x plus c, and we say x plus c is less than or equal to the L value of N7. The L value of N7 is still A plus F, so that's the relationship. And we also found a new edge. Okay, we found a new edge from N7 to N2. So here is N7, and here's N2. We draw a new edge here, call this J, and we found a shorter path. So this particular relation that I'm looking at right now is true. So we have to kind of keep track of that one. So so this is no longer A plus F. It is now J plus L of, so it's J plus H plus C at this point. And we also want to know that A plus F is greater than J plus H plus C. Because every single time we update an L value, it means the old value of the old L value is greater than the new L value. So every single time we do a cross out like this, it's telling us whatever we are crossing out is greater than whatever is replacing the crossed out expression. All right. So now we are down to N7 in Q. We pick out Q. We pick out N7. There are no incoming edges to N7. So N7 has no incoming edges. So that's here. So now we have the entire graph figure out as well as the relations. Do we have any questions about this part? Now, if somebody can give me this answer, just in terms of the variables without actual values, but the relation turns out to be correct, okay, that person is going to get full credit if all the steps are shown as what I have just displayed here. All right. So Anita is typing something. All right. All right. So the question is, okay, I cannot answer Angel's question, not because I'm not willing to, but because I'm not really sure what it is referring to. And obviously, once something comes out of my mouth, it is out of my brain. So it's hard for me to say something again because once I say it, it's no longer residing in my mind. About showing work for full credit. So if someone can show me, but sequence, all of these comparisons, because I kind of drew it all around the whole thing, but sequencing it correctly and also come up with the correct relationship, like what I displayed, in the graph here, that is worth full credit already. So I don't need exact values, to replace all of those expressions. To answer Anita's question, can I explain how we got A is less than I plus D? Okay, so A is less than or equal to I plus D is because A is the L value of N3. So somewhere along the line we chose 3 instead of some of the other vertices. Right? I think it's this one. Okay. So when we encounter this one, we at that point we conclude that the L value of n3 is less than the L value of n7. And I'm not really sure at that point, what we have found about n7, um, but that is not I plus d. What exactly is I plus d? I plus d is the. Oh wait, okay, never mind. Um, it had to do with the update of the L value of n3. So at some point we updated the L value of n3 right here. There we go. So Anita, this is how I came to that conclusion. Is because it is false. Okay, so if L of n3 at that point and L of n3 at that point is a is not greater than, which means it is less than or equal to. So that's how I establish at that point L of n5 is d, and then the distance between n3 and n5 is I. So this line here is how I came up with this link over here, that a is less than or equal to I plus d. Is that okay? Does that help? Okay. Now the more systematic way to do this is to do it using a trace. Yeah, you can rewatch the stream too. But the other way to do this is not to do it, using a graph and kind of more look at it kind of in this intuitive way. You still need this portion, okay? This portion you still need because, in order to uh, express the ordering, you still need to have a separate representation of what is less than or equal to what and what is greater than what. Okay, so that still has to be maintained independently. But if you look at the trace that we did on Monday, not Monday, last Wednesday, on the Dijkstra algorithm, so instead of using specific values, in that trace, you'll be replacing those specific values with, expressions like this: a plus f, g plus e, h plus c, and so on. So you would still be able to utilize a spreadsheet or a table to keep track of, what L value is having what. But when you're reconstructing that trace, you don't have to make the decision anymore because the decision is already made based on the trace itself. So as a result, you will still be able to come up with all of these relationships, except it is easier to keep track of what is in L of n2 because the trace itself would have that expression in L of n2 being g plus e at one point, and then we update it to h plus c at a later point. All right, so I would consider this as a as a perfect answer, 100% answer of this particular question. Now, if you want to assign specific values, you can. Okay, it's just that it is a little bit tricky to do that, because you have to figure out what is the smallest first. Okay, so how do we know what is the smallest? You kind of have to combine all of these relationships, to figure out what is the smallest, because we know a is less than or equal to e, and at the same time we know c is less than or equal to d, and we know e is less than or equal to c. So now we kind of have a link here. Okay, so let me see if I can explain this. So by combining a is less than or equal to c, c is less than or equal to d. So now we can extend this graph, quote unquote, tree graph, however you want to call that. And then we know e is less than or equal to c. So now we go like this. Okay, a is less than or equal to e is less than or equal to c is less than or equal to d. So that makes the graph a little bit easier to read because instead of having those segments, scattered all over the place, now we have a linear thing that says a is less than or equal to e is less than or equal to c is less than or equal to d. And now we want to look at d and see whether it's less than or equal to something, and the answer is yes. Okay, so it is less than or equal to a plus f. It is also less than or equal to h plus c, like that. All right. So by doing this, we can now, we can kind of ignore this subgraph here, and then C itself is also less than or equal to A plus F. But that is already established here, so that one is redundant. C is less than or equal to G plus E. So we look up G plus E and see if G plus E is greater than H plus C. So that is also established here. So now we extend this link to G plus E over here. But I hope you guys are starting to understand what I'm trying to do here. I'm trying to make everything in a linear fashion. So E and D, E is less than or equal to D, is also expressed here. So that part is already accounted for. So at this point, what about A plus F? A plus F is greater than or equal to C, so that is also reestablished here. G plus E and H of C. So that is also established over here because we can see there's a line over here. A plus F versus J plus H plus C. Okay, we're looking at this one here. So we can express that one here. So we can say this one, A plus F is greater than J plus H plus C. Right. No, the other way around. Let me see. We updated L of N7, so we know that one, the other one is shorter. Oh, okay. So we cannot do it this way. We take out this link, and then we express it like this. So H plus, okay, because H plus C plus J is less than A plus F. So that's why H plus C itself has to be less than A plus F also. So by doing this, and then we look at A plus F, is it less than or equal to something else? No, it's greater than, oh, okay, see, okay, I forgot that we got this, which is encoded into here. A plus F is greater than J plus H plus C, so we can, okay, I'll make this, I'll make a change here because I want to make sure that we capture every single piece of information here. Okay, so I'm basically re-expressing, the ordering, and this time, we can look at this linear line. So the only thing that is left is I plus D, but I plus D is also expressed somewhere, but it's independent to the rest. Let me double check. Yeah, so I plus D is only in relation to A. It is not in relation to anything else that I can tell. All right, so let me highlight the line that I think is particularly helpful. Okay, so A is less than or equal to E. E is less than or equal to D to C. C is less than or equal to D. D is less than or equal to H plus C. H plus C is less than or equal to H plus C plus J. That one makes sense because distances cannot be negative. H plus C is less than or equal to G plus E. H plus C plus J is less than or equal to A plus F. All right. But you can also see how A is all the way on this end, and then A plus F is all the way on the other side. So that tells you that F has got to be a pretty high value. A, you can make it as small, you can pick anything for A because it is the root, the starting point of everything. So A can be, I mean, do you guys still want me to kind of work this out, or do you think you're good? Because we are at the end of the lecture, but for those of you who want to kind of plug in actual values, we can do it. But if you don't want to do it, that's fine too. Okay, I think Jonathan is getting it. And what about the rest of the class? Not seeing anything. Oh, okay, here's Anita. Okay, you're good. Okay, very good. So this is basically, how to work out, this particular question. Um, Very good. All right. So I'm just gonna leave it as this, and this is our last lecture. Um, you can work out part of it on the Google Sheet. So you can reuse the approach that we did on last Wednesday when I worked out Dijkstra's algorithm. So you can work out. Okay, let me. Did I save that one? If we do that on the exam, can we add a link to the Google Sheet? Yes, you can. I believe you can copy and paste from Google Sheet directly into a Google document, so you can do that too. You can always just do that. You can also add a link, from your Google Sheet to the Google Doc to the Google Sheet. That works too. But I believe you can embed portions of a Google Sheet into Google Doc directly. So that's the other way to do it. Alrighty. Any other questions? All right. Yeah, so this kind of exam is very it's interesting to grade because I believe last semester I generated enough graphs, variants of this graph, so that each student has a unique configuration. Yep, I got a program to do that too. And Jonathan is typing something. So I'm pretty much done with the explanation here. Yes, so the exam is going to be everything after exam 2, and um, I do not want to ask any questions about complexity because that's more or less really kind of a concept thing. It would be I can ask multiple choice questions about that, about the definitions and whatnot, but it's not at this level. We are not doing a whole lot of applied analysis of the complexity of an algorithm. So that one, I kind of feel like I don't want to ask too much about it. Um, it doesn't mean that we cannot have questions about complexity, but it was still within the context of graphs, and yeah, it would be still within the context of graphs. Um, and the time complexity of both of these algorithms can be found using a Google search. So it's not going to be very challenging if I just ask, oh, tell me what is and derive the time complexity of A star algorithm. And people will just kind of go on to Google, search, copy, paste, and kind of be done with it. So that would not be a very meaningful question because when I ask a question in an exam, especially the final exam, I really want to make sure that that answer cannot be Googled. All right. So does that answer your question, Jonathan? Okay, cool. All right. So we are done with all the lectures, and I want to let you guys know that office hours are still ongoing. So every day between 11 and noontime, I will be holding my office hours. So if you have any questions, that would be a good time to ask. Because other than outside of my office hours, it can take a little bit longer for me to get back to you. But I am, in front of the computer during my office hour. And people would be asking, but don't you have Discord installed on your phone? Yes. But why don't you answer questions as they come in? Well, because I got a life too, just like the rest of you. Final exams are always 2 hours long, because it is scheduled in the um, final exam schedule. So the exact time for the final exam is according to the final exam schedule because this is a synchronous class, so it is almost as if it is just on the ground. All right. Any other questions? Yeah, so for the most part, it is kind of like a longer, exam, because exam 1 and exam 2 are 80 minutes long, and this one is going to be 2 hours long. I do not know for sure. I don't think it is starting at exactly noontime. All right, so here's something that you probably want to know as well is you can look it up. So you look up, okay, I'm gonna do it in the actual search box here. So you look up, okay, not spell, American River College final exam, and then you just look up that page. This is not an evening class, this is a AM class, daytime class. No, you cannot help me. I tried that already. It's next to useless. This Bucky mechanism is next to useless. Probably worse than useless because it's taking up screen space. It's almost like, being very, uh, I'm not going to go there. But it's taking up screen space, so it's worse than useless. All right, so the start time of our lecture is noontime, is exactly noontime. And this is a Monday, Wednesday class. So this would be, oh, okay. So this is going to be when our final exam is going to be, is on the 17th from 12:45 p.m. to 2:45 p.m. So it's 2 hour long, exactly as scheduled here. So are we good with the exam time? I'm going to type it in the text channel just to be sure. Okay, so final exam is on the 17th of May from 12:45 p.m. to 2:45 p.m. There we go. So it's going to be 2 hours long. So make sure you block it, in your calendar so that you don't accidentally forget there's a final exam, because in the past that has happened. Okay, there have been people who forgot to show up in the final exam, even when it was face to face on the ground. Okay, people forgot to show up for the final exam or show up late, and there's no accommodation. I'm sorry, there's no special accommodation for people who came in late or people who told me, oh, my alarm clock did not go off. I'm sorry, but there's nothing I can do, because we are all gonna take the exam at exactly the same time. Alrighty, so I'm gonna stop the lecture at this point. My office hours, as I said a little bit earlier, are still from 11 to noontime. So you can use that time to contact me. We can voice chat, we can video chat, we can just text chat, doesn't matter. But during that time, I'll be interactive. Alrighty, so I'll see most of you next Monday. But if you do have questions, don't hesitate to contact me, especially during the office hour. Alrighty, you guys have a nice weekend and study. Make sure you understand everything. Okay, I shouldn't say study. Make sure you understand, especially the algorithms. Okay, make sure you understand the algorithms, why it is designed that way. What each construct is doing. What is the purpose of each statement. Okay, the loops, the conditional statement, the updates, what are they doing? Why are we doing that? Those are the important questions that you kind of have to ask yourself. Alrighty, I'm gonna stop yakking now. Bye.